Okay, good morning. Here's a piece of advice. Do not ever Google sweaty people. Um, because a lot of nasty pictures come up. I don't know this person individually here, but I just pulled this picture. This is like a tame one off Google Images. Um, okay, so we talked about on Friday, or the day before, we talked about intermolecular forces and how that's a force of attraction that makes things stick together. I want to talk about how that affects phase changes. And so, one thing I would like you to think about is why you sweat. You have liquid coming out of your pores, and then on your skin, it evaporates. In order to do that, that water, that sweat, has to absorb energy from you. It has to increase in energy in order to break the intermolecular forces and turn into a gas. And that's how and why you feel cooler whenever you sweat. It's the same idea for when you put nail polish remover. If you go to take nail polish off, or if you put some on your skin, if you have some at home, it'll feel a lot colder than just room temperature tap water. Even though they're both at room temperature, it's absorbing energy and turning into a gas. So during phase changes, because you are literally changing the phase and breaking or forming intermolecular forces, it's a potential energy change. Inside the bonds that we have, there's energy stored, and we call that chemical potential energy. So whenever you are making or breaking bonds, whether they're ionic or covalent or they're intermolecular forces, it involves potential energy. Last time we talked about how temperature is a measure of kinetic energy. So any time that you see a change in temperature, the molecules are going to be moving either faster or slower. But during a phase change, we see that there isn't a temperature change. So I've got temp over here on the y-axis, and here if we look at whenever you boil water, what temperature does water boil at? 100 degrees Celsius at sea level. It stays at 100 degrees Celsius until all of the water has changed phase. So if you started with ice down here at the bottom, and you started to add heat to it, the molecules will start to move faster and faster, and then eventually you're going to hit what we call the melting point if I'm moving up this graph that I have here. During that phase change, all of the energy that the ice is absorbing is going to breaking the forces of attraction between the water molecules so they can now move kind of freely past each other. That's why ice water, where you've got ice and water together, stays at the exact same temperature, because all of that heat from the room goes to breaking those forces. And then once all of the ice is melted, then you see the liquid water start to warm up. And then eventually it gets so hot that all of the energy going in, oh no, my stupid cuckoo clock. Oh, okay, it was only once. All of the energy that goes into it goes to just changing the phase. And then once all of the water is totally boiled, then the gas is able to get hotter and hotter. So I just want to be really clear that anytime we have a phase change, whether we're adding energy or taking energy away, we don't see a temperature change because it's a potential energy change, not a kinetic energy change. And so the big piece from today is that during a phase change, intermolecular forces are either being formed or broken during that phase change, and there's no temp change. But anytime we break those bonds, so think of turning solid ice into liquid water, it always requires energy. We'll hit this a lot next unit too, but we have to add energy to get that to happen. If we want to take liquid water and turn it into a gas, we have to add energy to it. So breaking those forces always requires energy. Bond formation always, I don't remember what word I was going to place in there. Bond formation always, I'm going to say, requires a loss of energy, might be the better thing to put. You always lose energy to do it. So to take a gas, you need to slow them down in order for those intermolecular forces to come more in contact with each other to turn it into a liquid. we were going to do a lab in class where I was going to give you an unknown substance, and some of you were going to heat it, some of you were going to cool it. And what we noticed is that whether you are heating it, so here's our heating curve, we have that flat part, and whether we are cooling it, I just want to be really aware that that happens at the same temperature. So water's boiling point and its condensation point are both 100 degrees Celsius at sea level. We're just approaching it from a gain in energy and then a loss in energy. So big piece, changes in temperature corresponds to kinetic energy. That's the motion of the molecules are increasing if the temperature is increasing. But a change in phase corresponds to potential energy. So I think I'm going to stop here today. Next time I see you, we'll talk about some variables and why we treat gases completely different as far as the chemistry involved. But I would like you to try the homework assignment then for today.